begin formally now. So good evening. Today's session's on structure and bonding. It's a revision of some of the key ideas that you need to know about structure and bonding for A-level. Only some of them. It will take too long to do all of it in just an hour or 15 minutes. So it's just a bit of an introduction of some of the key things that you need to be aware of. We're going to look at different types of bonding and how they arise, what causes one bond to be different to another, and how the type of bonding within a particular material affects the physical properties of that particular substance. So we're going to begin with covalent bonding. I'm sure you all know what a covalent bond is. It's a shared pair of electrons between two atoms. I'm sure you already know this. The reason I've started here is because essentially, you know what a covalent bond is. We don't always understand how a covalent bond holds two atoms together. If two atoms are sharing a pair of electrons, what you have is an electrostatic force of attraction. And it's electrostatic force that occurs between the positively charged nuclei and the shared pair of electrons. It's the type of thing that might get thrown at you in an exam, and it just trips people up. How does a covalent bond hold two atoms together? It's sometimes taken a little bit for granted, and it's just something that you need to be aware of. Now, of course, not all covalent bonds are the same, and the reason they're not the same is because we have this property of an atom called electronegativity, and electronegativity can cause a covalent bond to undergo a process called polarity. Now, definition of electronegativity is one that not only you need to know and be able to reproduce, but you need to be able to understand it as well. The wording of the definition sometimes changes a little bit depending upon which textbook you read. In an exam situation, you were given a little bit of leeway in that case, but essentially it's the power of an atom to withdraw electron density from a covalent bond. So you need to refer to atom, you need to refer to electron density or shared electron pair. The power of an atom to attract the shared electron pair in a covalent bond would also be an acceptable definition too. It's one of those definitions that you have to be careful with. You have to be really clear with. So essentially what we're saying is that when atoms covalently bond, some of them have a stronger attraction to the shared pair of electrons than others. And there are reasons for that, which I'm not going to get into today. We'll maybe cover that another time. And the whole point of this, of course, is that this means that the shared pair of electrons between the two atoms, they have different negativity. I'm not going to include them. So electronegativity, it varies throughout the periodic table, and I'm not going to get, as I said, I'm not going to get too much into reasons for this today. We might leave that for a different session. Eventually, it's related to the nuclear charge and the distance between the nucleus and the outer shell of the atom. The trend is that as you go towards the top right-hand side of the periodic table, the electron negativity increases. I should point out, by the way, if I say anything at any point that doesn't make any sense, you're welcome to use the live chat just to ask a question. That's absolutely fine. And I will check them from time to time. So as we move towards the top right-hand side of periodic table, the electronegativity increases. Of course, noble gases are nominally not given electronegativity values, and that is because under most circumstances they don't form covalent bond. That's not strictly true. Some of them do, and some of them are given nominal values, but for A-level chemistry, it's not something that you have to be concerned about. There is a rule of thumb where the difference in electronegativity of the two atoms that are bonding can be used to determine what type of chemical bond you're going to get. It's only a rule of thumb. It doesn't work perfectly in every case, but it can give you a general idea. One of the ones to definitely be aware of is that a difference of 0.4 or less will give you a non-polar covalent bond. So if I was to just go back for a second, we take the example of carbon on the top. The second period, towards the right-hand side, carbon's electronegativity is 2.5, compared with hydrogen at the top left, that's 2.1. So they have an electronegativity difference of 0.4. There's a difference. It's not classed as a difference to make them polar, and that's why your hydrocarbons like alkanes and alkenes, for example, are classed as non-polar molecules. If you have an electronegativity difference between 0.5 and 1.6, then you have your polar covalent bond, where the electron density is more strongly attracted to the atom that has a greater electronegativity. If the difference is greater than 2, then you get an ionic bond. Now you might be thinking to yourself, well, there's a bit of a gap there between 1.6 and 2.0. Well, again, as a general rule of thumb, if the electronegativity difference is between those two values, if a metal is involved, it will frequently be ionic. If a metal is not involved, then it would be a polar covalent bond. Now, I say that this is a rule of thumb. It's not a hard and fast rule, and there are exceptions that arise. But as far as A-level chemistry is concerned, you can treat this as with a reasonable level of confidence as the type of bond that you will have in all of these cases. There are notable exceptions. Aluminium chloride, for example, is classed as being covalent rather than ionic. That would be a good example. The electronegativity difference is 1.5, which would lend it to being polar covalent. But of course, because it contains a metal, at GCSE, I think you're normally told that if a compound contains a metal and a non-metal, it's always going to be ionic. Not always. There are exceptions. Aluminium chloride is a good example of one of those exceptions. Beryllium chloride is also covalent too. The electronegativity difference there being 1.4. So, I'd already said you've got the difference in electronegativity, which leads to the type of bonding that you get. And as a result of this, your electron pair will not be evenly shared. So in the example of a chlorine-chlorine bond, the electron pair will be exactly, on average, halfway flattened, because there is no difference in electronegativity. You can think of the shared pair as being a sort of war, and both atoms have equal pull on that shared pair. So they won't be on average closer to one atom than the other. But in the case of hydrogen and chlorine, hydrogen's electronegativity is 2.1 and chlorine's is 3.0, which means that chlorine's electronegativity is greater, and the electron pair will hold closer to chlorine than to hydrogen. As a result of this, you get what we call your dipoles, which we represent with our lowercase delta. The Greek T indicates which atom is slightly electron deficient and which atom it is slightly electron rich. Now, in the case of sodium chloride, the electronegativity difference is so great that it doesn't form a covalent bond at all. What actually happens is that sodium loses its electron altogether. Chlorine. And what we end up with is a negatively charged ion. And a positively charged ion, we have an ionic compound. And ionic compounds have very, very different properties to compounds with covalent bonding. We're not going to get into intermolecular forces which arise as a result of polar bonds today. That's one that perhaps will be covered, and maybe a little bit next week when we look at shapes and molecules. So what we're going to do now is go through each type in turn, just review some of the key properties that you need to be aware of, beginning with your ionic compounds. One of the things that you're expected to be able to do at A-level is work out the formula of an ionic compound without the list of ions that is usually supplied on the data sheet of GCSE exams. You will not have access to that anymore. It will be purely based upon your own knowledge of the charges of the ions. You are expected to know those. Key things to remember: your group 1 elements. Hydrogen is not a group 1 element, but it is put in there in terms of the charge of the ions. They're all +1. Your group 2 +2, your group 3 +3. Group 4, tin and lead form ions. The others don't tend to as much, so we don't worry about those too much. Group 5, -3, group 6, -2, group 7, -1 ion. So what you need to be able to do is to work out the formula of an ionic compound by balancing out charges. So, a couple of examples: sodium chloride, sodium's in group 1, so it's +1, chlorine's in group 7, so it's -1, +1 and -1 cancel out right away, so you just need one of each. Sodium oxide, well, sodium's obviously still in group 1, so it's +1, but oxygen is in group 6. So, because it's in group 6, it has a charge of -2, which means that to get the charges to balance, you need 2 sodiums. Sodium nitride, nitrogen being in group 5, forms a -3, so you need 3 sodium. And then aluminium, of course, being in group 3 is a +3. Chlorine's in group 7, it's a -1, so that's, you need 3 of those to cancel out the charge from the aluminium. For aluminium oxide, a little bit more complex, because aluminium being a +3 and oxygen being a -2, in order to be able to get the charges to balance, you need to change the numbers of both of them. 3 lots of -2 charges gives you a charge of -6 coming from your oxides. 2 lots of +3 charges from the aluminium gives you a total charge of +6, so they then cancel. And aluminium nitride is just AlN. Okay, an opportunity for a little bit of audience participation then. Using the periodic table, and I've taken the charges away, I am going to send you the opportunity to answer this particular question. The choices are A, B, C, and D. I have sent you a poll. What I would like you to do as quick as possible is click A, B, C, or D to indicate which one you think is the correct ionic formula. See if you've got the hang of this. A, B, C, or D, which one is right? Okay. So we've got some responses in. The answer is B, MgO, because magnesium is in group 2, so it's +2. Oxygen is in group 6, so it's a -2. You only need one of each to cancel out the charges. I'm going to do one more. This time it's magnesium nitride, a slightly trickier one, but the kind that you could expect to be asked at A level, where they're going to really try and test you. In fact, it was a question in a roundabout way a couple of years ago. So again, same as before, I've just sent you a poll. A, B, C, or D, they're your 4 formulae. I'll give you a few seconds. Okay, so the answer to this one then, well, magnesium is in group 2, so it has a charge of +2. Nitrogen is in group 3, so it has a charge of -3. The only way you can get those to cancel out is if you have 3 magnesium ions and 2 nitride ions. 3 times +2 is +6. 2 times -3 is -6, and then they will cancel out. Okay, so B +2, so we'll move on now. We'll move on to the actual properties of ionic compounds. The structure is a network, a 3D network known as a lattice of alternating positive and negatively charged ions. opposites attract, as the saying goes, so you have an attraction between positively charged sodium ions and negatively charged chloride ions, and for all ionic compounds, they repeat in a very specific pattern. The patterns can change slightly from one ionic compound to another, but there is a very specific repeating pattern. Thinking about what happens to them as we increase the temperature, well, in the solid state, those particles are in fixed position as they can't move around like all particles in solids, and the attraction between the positive and negative ions is relatively strong. It's an electrostatic force of attraction. You can call it an electrostatic force. You can call it an ionic bond. But be careful use of the words here. It is not molecular. You mustn't use the word molecular when you're talking about an ionic compound. It's not molecular. It's not molecules. If you're asked to talk about ionic bonding in the exam and you refer to molecules, you'll be penalised very heavily. So it is an attraction of positive and negatively charged ions as an electrostatic force. If you increase the temperature sufficiently, then those ions will start to move around in a liquid state and will take on liquid properties. If you heat them up even more, then it will become a gas. The ions will become completely free to move. You'll have an ionized gas. Many ionic compounds are soluble in polar molecules, like, for example, water, but not all soluble. It depends upon the strength of that ionic bond, and sometimes it can depend upon the relative sizes of the different ions. At Year 12 level, you're not required to get into too much detail about that, so you're just expected to know that some of them are soluble, and some of them aren't soluble, depending upon, mostly, for the most part, the ionic bond itself. And when it dissolves, you end up with a big mixture of molecules and ions. The water molecules essentially act to ensure that you have a homogeneous mixture, a fairly evenly spread mixture of positive and negative ions within the solution. Another property of ionic compounds, comparing them with metals, I'm sure you're all familiar with the diagram at the top. For a metal, where you'll know that metals are malleable and ductile, because if you apply pressure to the layers of metal atoms, they will slide along with no loss of bonding. If you look at the diagram underneath of the ionic crystal, if you apply pressure to that top layer that's indicated, what will happen is that you'll cause the ions with the same charges to line up, as shown by the one on the right. The moment those ions of the same charge line up, they will repel because they have the same charge, so they'll repel. That has the effect of making ionic compounds very brittle. They'll break apart very, very easily, very quickly. So just a summary of the different properties then that we've covered. They have high melting and boiling points because you have to break all of those strong electrostatic forces. Electrical conductivity we didn't talk about just then. You've probably covered this before, but just to recap. In the solid state, the ions are in fixed positions. They're not free to move, so they can't carry electricity. But the moment you melt it, the ions then become free to move, and they can then conduct. In order for any substance to be able to conduct electricity, it needs to have charged particles that are free to move. In the case of an ionic compound, it's the ions that need to be free to move. This is another area where you can be penalised very heavily if you're careless in the exam. It's nothing to do with electrons. When we think of electrical charge and current, we automatically think about electrons because when we think of the things that power our electrical appliances, these power supply would be a battery or it would be a mains, you plug it in, and it's a flow of electrons that supplies the power. But in the case of an ionic substance, all of the electrons are in full shells around the positive or negatively charged ions. The electrons are in fixed positions around those ions. They don't move, they don't migrate, they don't do anything, they just stay there. It's the actual ions that become free to move, and it's the actual ions that conduct. So if you are asked about in an exam about the electrical conductive properties of an ionic compound, you need to refer to the ions and whether the ions are free to move or not. Whatever you do, don't talk about electrons, or you will be punished heavily. They are brittle materials. the reasons I just said a moment ago. If you cause the ions to line up, the like charges join up and then they repel. And the solubility in water, it depends. Some of them are very soluble in water, some of them are not so soluble in water. It depends upon a combination of the ionic bonds and the size of the ion present in the ionic compound. Okay, yeah, that's absolutely fine. The recorded version will be available in the next day or two, so you'll be able to catch up then. Okay, so we'll carry on then. Your simple molecules, simple molecular substances. Your simple molecules occur when you have what we would call a finite molecule, where atoms form covalent bonds with other atoms in such a way that all of the atoms have a full outer shell in a discrete unit. For example, a molecule of methane, CH4. They also follow the properties of states of matter, solids, liquids, and gases. So in a solid, they take fixed regular positions across together. In a liquid, gain some kinetic energy. They can break some of the intermolecular forces that hold them together, and they can move around. And then in the gas, they are completely free of the intermolecular forces, and they are completely free to move. It's very important that if you are asked about change of state from solid to liquid to gas, that you refer to the intermolecular forces that are being overcome, intermolecular forces that are being broken. If you start referring to bonds being broken, again, you'll be penalised very, very heavily, so don't do that. Water is another classic example that you need to be aware of. We're not going to get too much or at all into hydrogen bonds in today. We'll leave that for another time. But hydrogen bonds are the intermolecular force that are present in water molecules. In solid, every single molecule is hydrogen bonded to other molecules. In liquid, some of the hydrogen bonds are broken, so they can move around a little bit. And then in the gas, they're completely free to move apart, so the hydrogen bonds are overcome. And again, like I said before, you must refer to the hydrogen bonds or intermolecular forces that are being overcome here. Iodine is another example that you need to be aware of. So again, in the solid state, the iodine molecules form a regular pattern. Again, a type of 3D lattice. And just like before, iodine in the solid has a regular pattern. In the gas, the molecules are free to move. I've also referred to liquid. I put question marks in there because you might be thinking, well, doesn't iodine combine? Doesn't it go straight from solid to gas? It does at atmospheric pressure. If you apply sufficient pressure to it, then you can get it to form the liquid state. The only reason anything forms liquid state is because the pressure for that substance is sufficient for it to do so. For any substances that supplying simply do not have sufficient pressure to hold them together in the liquid state. And that's to do with the strength of the intermolecular forces present in the liquid. Some substances do not have very strong intermolecular forces in liquid state, and that allows the particles to break together and it doesn't form a liquid. This idea was used in an exam from question from last summer that we're going to have a look at the end. But essentially the thing to bear in mind is the temperature range of the liquid state. If the liquid state has a temperature range, then you know that the forces present in the liquid are relatively strong. It has a very, very small temperature range in the liquid state, or perhaps no liquid state at all, then you know the forces in the liquid state are much, much weaker. Okay, quick summary then. Melting and boiling points are low because of the intermolecular forces between molecules, and you must refer to intermolecular forces, not to bonds between molecules. That would be wrong and would be heavily penalised. They are non-conductors because they do not have charged particles that are free to move. The electrons present in these molecules are involved in ionic bondings or in electron shells around the atoms. The electrons can't migrate between molecules or in fixed split positions in the atoms, so it can't conduct. Ions do not apply here because they are not ionic in nature, so you would not refer to ions when you talk about electrical conductivity of the molecule. Unless it was a molecular ion, and unless it was in solution, you were doing electrolysis on it, then maybe you would. Apart from that, that would be ionic in nature anyway. So you wouldn't do that. As far as we're concerned, for molecules that are non-conducting or very, very poor conductors. They are again brittle, purely because of the molecular forces between molecules are very, very weak. Their solubility in water is one that depends again. It depends upon the polarity of the molecule itself. If the molecule has polarity, then it may be soluble a little bit. If the molecule has the capacity to form hydrogen bonds, that would be an indication that it probably would be quite soluble, as long as it didn't have a really, really long carbon chain or something, which might give it some non-polar qualities. This is something that perhaps we'll get into in another session. Okay, so ice, water in the solid states. You've got your what we call your perfect hydrogen bonded system here, where every water molecule wants as many hydrogen bonds as it possibly can. And the interesting thing is that in the perfectly hydrogen bonded state, the water molecules are kept a very specific distance apart. Once you start overcoming some of those hydrogen bonds and some of the water molecules are free to move, you can actually get a little bit closer to each other than we can in the solid state. That's why water is so unusual, in that it is more dense when it is frozen. Because in the solid state, the water molecules are kept a very specific distance apart by hydrogen bonding. When it melts, the molecules can actually get a little bit closer to each other. It's an unusual property of water, but one to be aware of. Okay, moving on. Macromolecule, also giant covalent substances, as they're also known. Silica is a classic example of one. It has the empirical formula SiO2, but in actual fact, every silicon atom is covalently bonded to many oxygen atoms, much like this. So the silicon atom in the middle is bonded to 4 separate oxygen atoms. The oxygen atoms are bonded to 2 silicon atoms. And if you were to take a sample and count up all the silicon atoms and the oxygen atoms, you find that the average ratio is 1 silicon to 2 oxygens, and that's why we give it an empirical formula of SiO2. Diamond is another classic example of a macromolecule. Worth pointing out, macromolecule, a little bit misleading. They are not molecules as such, they are potentially infinite. They could, in actual fact, go on forever. Don't do. In the case of diamond, it's made of carbon. It's made of carbon atoms that are tetrahedrally bonded to each other. So each carbon atom bonds to 4 other carbon atoms. What actually happens on the very, very edges of the diamond is that those carbon atom bonds get terminated usually by hydrogen. You've got hydrogen atoms joined to the carbon atoms at the very, very end. So if you touch a diamond, you're not actually touching carbon at all. You'd be touching hydrogen instead. That's why diamond doesn't actually go on forever. It is finite in nature. The properties, well, they have very high melting points, because the only way you can get these things to melt is if you can break all of those strong covalent bonds. You have to break them all to get it to change states. And those bonds require lots and lots of energy. So you must refer to the breaking of covalent bonds when it comes to a change of state here. They do not conduct. They have no mobile charged particles. They have no electrons or delocalized electrons that are free to move. Electrons are all in the outer shell of atoms or covalent bonds. They're not migrating through the material. Clearly, there are no ions here. If you were to talk about ions when discussing the electrical conductivity of a macromolecular molecule, they're heavily penalized, so don't do it. They're very strong, for the same reason that they have high melting points and boiling point. All of the atoms are held together by strong covalent bonds. It gives it a very rigid, a very thick structure. So it is quite hard to change that structure. And it tend to be very insoluble in water, because they tend to have largely non-polar characteristics. And of course, you've got the very, very strong bonds, which require a lot of energy to break. The other classic macromolecule that you need to be aware of is graphite. It is another form of carbon, what we call an allotrope of carbon. Allotropes are different forms of the same elements that arise because of different types of bonding. In diamond, every carbon atom bonds 4 other carbon atoms. In graphite, it bonds to 3. That leaves each carbon atom 1 electron left over. That's not involved in bonding. And they delocalize within a layer and can move within a layer that allows graphite to conduct electricity, which is unusual given that it is a non-metal. We use it in pencil because if you run a pencil across a piece of paper, essentially what you are doing is you are breaking the weak forces between the layers, and that causes the graphite to spread out onto a sheet of paper. But just a quick summary then, they tend to have high melting points because you still need to break all the strong covalent bonds. Separating the different layers does not have any bearing in terms of the melting point. It's still solid. If you take that graphite and you grind it up into a powder of graphite, it's still solid. The only time you can get it to change state is if you increase its temperature and break all of those bonds. Diamond and graphite tend to sublime as well. We don't really tend to form a liquid state at all, look like iodine. Graphite, of course, does conduct because those electrons move within the layers. They don't really move between the layers, they just move within the layers. They bristle because of the weak forces between the layers that allow them to slide over each other, and they are insoluble, again, due to partly a lack of polarity and most of the fact that all those bonds are so strong, the molecules can't really get in there and break them up. Now, the miracle substance that you've probably heard about is graphene. In many ways, it's not that remarkable. It's just a single layer of graphite that's been made into essentially a single sheet of carbon. Has incredible properties, transparent, it's two-dimensional, incredibly strong, excellent conductor, lots of very good, some quite entertaining videos about possible applications of graphene on the internet. You might want to check those out. So we'll run through the properties of metals then, lots of the materials we'll look at today. Our metallic structure, it is our layers of metal atoms, or metal ions if you like. You can call them either really, with what we call our sea of delocalized electrons that move between all of those different metal atoms or ions. And that gives the metal very specific properties compared to all of the other materials. The metal layers are arranged in very specific patterns, so that's slightly different patterns. You have the regular layers, but how the layers arrange and isolate, whether they can get closer or further apart, varies from metal to metal. It's not something you have to be too concerned about at A level, though. The main thing you need to be aware of is that the metal atoms are arranged in layers. And as we said before, compared to ionic compounds, a layer of hot atoms, metal atoms, will slide along. And because you have the delocalized electrons kind of acting as a glue or as an electrostatic force between the positively charged metal ions, that sea of delocalized electrons is not disrupted by changing the layers and the positions of the layers. So you can bend a metal, you can stretch a metal, but it will still retain its strength. That's the thing that makes metals highly malleable, i.e. bendable, and highly flexible. You can stretch them, you can pull them into layers. So summary of the properties then. They tend to have high melting points and boiling points, not all of them. Gallium's a classic example, a melting point of about 30 Celsius. It will actually melt in your hand if you handle some. Most of them do have high melting points though, and that's because of the strong attraction between those ions and delocalized electrons. And you must have to refer to electrostatic force of attraction between them. Don't talk about ionic forces. It's an attraction between the metal ions and delocalized electrons. If you refer to an ionic force, it sounds a bit too much like ionic bonding, and you're likely to get penalized again. They are good conductors because of those outer shell electrons that are delocalized and completely free to move throughout the structure. That's what makes them very, very good conductors. They are strong because the layers, although they will slide, the metal retains its strength because of the metallic bonding. The metallic bonding is not disrupted by changing the shape of the metal, and they are insoluble in water. Okay, so a couple of quick quizzes then, just to check how much of that's we've managed to follow. So just like before, I'll send you the whole 4 different types of bonding. Properties given, and you determine from those properties the structure would be the correct structure. Okay, so the answers are in. That one would be ionic, because the melting points are relatively high, which would rule out the simple molecules. It doesn't conduct in the solid state, but it does conduct in the liquid state. That's the big giveaway for an ionic compound. They're the only ones that tend to conduct or not conduct in different states of matter. Okay, so here is the next one. Oh, I think I've accidentally run over that one. I clicked a bit too quick. We'll just I'll just go through it. So low melting point, low boiling point, complete non-conductor, low melting and boiling point. That will be a simple molecule. We'll try the next one then. The properties are given there. The whole is on its way. So you've got your properties as they appear on the screen. So the answer is in. Yeah, we have a high melting point, high boiling point, non-conductor, insoluble. Clearly that's going to be a macromolecule. 1 or 2 more. Okay, the answer's in. 2.135, 1.215, total non-conductor. Yeah, that would be a simple molecular substance. Solid at room temperature. Many simple molecules are actually solids at room temperature. Good examples would be phosphorus and sulfur. Okay, here is your next one. That might not be the best one. Hopefully you can read it reasonably well. Okay, coal is on its way. Okay, so the answer is in. Yeah, high melting point, high boiling point, conductor in solid and liquid state, insoluble. That would indicate it's almost going to be metallic. Okay, so just to round things off then, this is a past paper question that came up in the exam last summer, and it relates to structure and bonding. Some information was provided on the elements bromine and magnesium, the melting point and the boiling point. And the question for 5 marks was, in terms of structure and bonding, explain why the boiling point of bromine is different from that of magnesium. Suggest why magnesium is a liquid over a much greater temperature range compared to bromine. So the key thing here is to refer to the correct types of structure and bonding. We're referring to boiling point, so we must talk about the forces that prevent the particles from moving apart and becoming a gas. You must refer to the correct types of forces. But bromine is simple molecular, so you must refer to intermolecular forces. Magnesium is metallic. You must refer to metallic attractions, metallic bonds. And that's how you have to approach the question. So just to skip one by accident, to go through the mark scheme very quickly. So 1 mark for just identifying that bromine is its intermolecular consists of simple molecules. 1 mark for identifying that magnesium is metallic. 2 marks out of 5 just to be able to do that. Then you need to refer to the forces between the particles. So if you said that bromine has weak forces between the molecules or weak molecular forces, a mark, fine. So more energy is needed to overcome the strong metallic bond, or the opposite, the comparison would be direct or implied. So if you said that magnesium has metallic bonding, which is much stronger than the weak intermolecular forces in bromine, that would qualify for Mark 4 and Mark 3. That would be fine. The one that tripped up an awful lot of people with Mark 5, this idea that part of the question, why is magnesium a liquid over a much greater temperature range compared to bromine? You can see that bromine's temperature range 266 to 332, much smaller than magnesium, 360 or 460, sorry, I can't add up scale one day, 460 degree difference there. So you need to talk about the fact that refer to the forces within the liquid substances. So the force of attraction in the molten metal must be stronger than the force of attraction in liquid bromine. Tripped an awful lot of people up that particular mark, and I marked an awful lot of these, and very, very few candidates managed to secure that mark. So I'm going to finish with one last question for you. This was the report by the examiner, and yeah, many chemical errors. Just to go back a second. So I'm asking, if there was a reference to breaking of covalent bonds in bromine, that lost Mark 3 and Mark 4. If there was a reference to the wrong type of bonding in magnesium, molecules or ionic, that lost 2 and 4. So any reference to the wrong types of bonding was very, very heavily penalised. Chemical error penalties, where you actually make a statement that is chemically incorrect, they are penalised very harshly. On a question like this with a number of marks, they typically carry a penalty of 2 marks. And those 2 chemical errors, they carry a penalty of 3 marks altogether. So here was the report by the examiner, and yeah, many chemical errors. Simple molecular pointers absent for both weak and strong students, showing for some technique in terms of addressing the question. It was not a very well answered question. That's the general view. So finally, one last question then to conclude the session. I'm interested to know if you could tell me what you think the nearest mark, what was the average mark out of 5 scored by all the candidates who took this, and there were over 20,000 of them. What do you think was the average mark scored out of 5? Of them. Okay, the suggestion is 3. The average for all of them was 2 1/4. So 2 out of 5. It was not a very well answered question, but for a candidate who is hoping to achieve one of the higher grades, it's the type of question where you can personally gain an advantage with by being really clear on your definition of structure and bonding. That's really the take-home message today. When it comes to structure and bonding, make sure you know your stuff, and make sure you get your definitions absolutely spot on. So I'm going to conclude the session here today on structure and bonding. I hope you found it useful. I will gratefully accept any feedback at all on how I can make this particular service better. So thank you very much for that.